Hello, this week we are talking about paleo archives. Paleo meaning really, really old, and think geologic, millions of years ago, and archives meaning, right, records, what happened. So, what the climate was like a really, 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 really long time ago, and how we can use that information from the geologic past to interpret and predict what's happening today. Okay. So, let's get into it. Here we go. So, information from the paleo archives. So we know that today, current global warming is unprecedented over the last couple thousand years. We know this because we have records, right? Humans have been around measuring, you know, what the temperature is, how much precipitation there is, all of that. We also have written records, even though people in the past might not have had, like a thermometer or anything like that. They could say, man, it's like abnormally hot today, abnormally cold today. We see ice today. We don't see ice today. So we could get an idea of what the weather was like over human history. However, right, just because we know that the current rate of global warming is unprecedented over the past couple thousand years, if we look at this graph, you can see that, right, as we've discussed, we are about 1 degree Celsius warmer today than we were 100 years ago. And over the past 2,000 years, the climate, the temperature has been pretty steady until we get to modern times. But how do we know if this is any different than what's happened over the entirety of geologic history, right? Is what we're seeing today totally unprecedented ever in Earth's 4.6 billion years? Or is this just like a natural thing that happens periodically and, shouldn't really alarm us, right? So in order to do that, we have to know what the climate was like millions of years ago. We have to be able to reconstruct paleoclimates. And how do scientists do this? If we weren't around a million years ago, how is it possible for us to know what the temperature was like? Well, there's several different ways that we do this. The first way is with ice cores. So ice cores that come from glaciers and ice sheets record what the climate was like in the past, right? So if you go to Greenland or you go to Antarctica, you'll stand on that ice sheet, and the ice that's on that ice sheet is a buildup of ice from, thousands and thousands of years ago, where every single year, another layer of ice is deposited. The next year, another layer of ice is deposited. The next year, another layer of ice is deposited. And within each of those layers of ice is trapped air bubbles. And those air bubbles are perfect little records, perfect little preservations of the atmospheric chemistry when that layer was deposited. Because that little air bubble, right, captured the atmosphere when it was created and hasn't changed, hasn't been exposed to the modern atmosphere ever since then, right? So those air bubbles are perfect little time capsules of what the atmospheric chemistry used to be like. So we can use ice cores to look up how much carbon was in the atmosphere, how much methane was in the atmosphere, and try to figure out, what would temperature be with that atmospheric concentration of those greenhouse gases. Now, this is fine and dandy, and we use this a lot. However, this only lets us construct paleoclimates to the point of our oldest ice sheet on Earth. And we know that in Earth's geologic past, sometimes all of the ice sheets melted, right? So we can't go beyond that. We can only construct paleoclimates up to the oldest ice on Earth. So ice cores are not the only way that we interpret paleoclimates or we construct paleoclimates. We have other, what we call proxies. Proxies are just like a way for us to figure out what the temperature was even without a direct measurement. And those other proxies are marine oxygen isotopes, fossils, rocks, and minerals. So a picture that you're seeing here is of what we call a foraminifera. It is a marine plankton, a tiny, tiny little plankton that floats around in the ocean. And this little foram, as it is building its shell, which we call a test, as it's building its test, it's taking in the chemistry of the seawater into its test, which is calcium carbonate, right? Just like an oyster shell, just like a clam shell, it's calcium carbonate, and it's formed from the elements in the ocean water. And we know that the composition of the ocean water, the chemistry of the ocean water, varies based on the temperature of Earth. So for example, when the temperature of Earth is very, very cold, then you're going to end up with a higher amount of the isotope oxygen 18 as compared to oxygen 16 in ocean water. Whereas when the Earth is very warm, you'll get more oxygen 16 in the water compared to oxygen 18. And because of this, right, because the sea chemistry changes, the chemistry of the test is going to preserve the chemistry of the ocean water. And when these forams die, they sink to the ocean floor, they become preserved there. And if we then go to the ocean floor, dig up these, fossil foraminifera and test their shells, we can figure out, oh, when this shell was alive at this time period, this is what the ocean chemistry was. So this is probably what the temperature of the ocean was, right? So using fossils, marine oxygen isotopes, we're able to do a ton of reconstruction of paleoclimates. This is actually the main way we reconstruct paleoclimates, is with marine oxygen isotopes and foraminifera fossils. We can also use rocks and minerals, right? As we've talked about in previous geology classes, right? Limestone is typically formed in warm environments. Coal is typically formed in warm environments. Glacial erratics are only deposited during cold environments, right? So we can look at the rocks and minerals that are present and know in general what type of environment had to exist. We can't pinpoint the exact temperature like we might be able to do with foraminifera, but we can get an idea of what had to be around. Right. And by doing this, by looking at ice cores, marine oxygen isotopes, fossils, and rocks and minerals, we can reconstruct the temperature of Earth through time.